will discuss enthalpy. And if I can find the freeze button. Aha. So today we will discuss enthalpy, and enthalpy is the total sum of energy inside a compound. All right, and again, remember, it takes energy to keep the electrons from crashing into the nucleus. Remember we said that if we put more energy into a compound, its electrons moved out, and as they move closer, it releases energy. So this is the energy that holds its electrons away from its nucleus. This is all of the energy that holds the electrons in bonding orbitals, which require a lot more energy than just base orbitals around. All right. So as soon as you make an sp3 hybrid orbital, or an sp2 hybrid orbital, that requires more energy, and that energy is now inside the compound. All right. And this is cannot, for practical purposes, this can't be measured. Which that's a bit of a simplification. But the point being, we are never going to measure in this class the enthalpy of a compound, because the enthalpy is the total sum of the energy inside of it, and we do not have a technique or a set of tools for measuring that. Does that make sense? We would have to measure the energy involved in every electron orbiting that atom, and that's just not something we're able to do. All right. Remember, chemistry is really all about electrons. Lots of electrons involved in a compound. You'd have to know the average energy involved in every one to measure enthalpy. We can't measure this. What we can measure, so enthalpy is H. We can measure delta H. And delta H would be what? Good. We can't measure enthalpy, but we can measure its change. Imagine this. If you are on the road, on a highway in the middle of nowhere, there's no street signs and no markers. Can you know your position, where you are? If you have no idea, you're dropped in the middle of nowhere in your car, you have no idea where you are. Do you know your position? No, that information isn't available to you. But if you have an odometer, can you measure your change in position? Sure, that's just how far you drive, right? We can often measure the change in something when we can't measure the thing directly. In fact, we talk about temperature. For a long time, we didn't know about absolute zero. We could only measure temperature in relative terms. Later on, we discovered what absolute zero was, but it's often easier to measure the change in something than to measure the overall value of the thing itself, right? Another, I think, kind of analogous level, we have no idea what the total volume of ocean water on Earth is, because it would involve having to know the depth of every trench, and it would involve knowing every crevice that runs under the bottom of the ocean floor. We have no idea what the total volume of the ocean is, but we can measure its change in volume quite easily just by measuring the change in the height of the ocean level. Does that make sense? So there's things where we can measure the change where we cannot measure the total value. Enthalpy is a good example of that. We do not know how much energy is in all of those bonds, but we can measure it when it changes. The reason being, when it changes, that energy either has to come into the system, right? It either has to remove energy from the surroundings into the compound, in which case we could measure how much energy is lost in that surrounding system by how much the temperature goes down, or we could do a chemical reaction and it will release heat, and we can measure how much the temperature of the surrounding system goes up. And then we will have measured how much energy was released. Does that make sense? So even though we can't measure the starting enthalpy, we can measure the change in enthalpy. And we do this for a series of reactions. Any reaction, we can measure how much energy change is involved. We don't know how much energy the chemicals that started had. We don't know how much energy the chemicals that end have, but we know the difference between them. We know the difference between them. There we go. This is an example. By the way, as a convention, we always measure, or we always endeavor to measure, molar enthalpies. What does that mean? What's a mole again? 6.02 times 10 to the 23rd or something. Very good. Does that ring a bell? Yeah, 1 mole of something is 6.02 times 10 to the 23rd. Now that's an esoteric number. That's a huge number. It's a lot of them. But it's special because it means if I have a mole of, I don't know, hydrogen, what will I know about that? This is why that number is meaningful. A single hydrogen atom weighs 1 atomic mass unit. If I have a mole of them, how much will it weigh? 1 gram. We like the mole because it converts from atomic mass units to grams, right? So if I have a mole of hydrogen atoms, it'll weigh 1 gram. Hydrogen gas is made of 2 hydrogen atoms. So if I have a mole of hydrogen gas, it will weigh 2 grams. So as an example, if I took 2 grams of hydrogen gas, I would have a mole of it. That make sense? If I burned a mole of hydrogen gas, I would have to use half a mole of oxygen. I know that normally we would never put a fraction in a chemical reaction, but in this case we have to, because when we talk about molar enthalpies, we're talking about using 1 mole of this stuff. So I just have to divide everything by whatever I have to divide it by to make that work. So for every 1 mole of hydrogen I use, I would have to use half a mole of oxygen. Does that make sense? Because it's got 2 oxygens on it, but I only actually want 1 of them. Now, that in and of itself doesn't work, right? We would have to actually double the reaction, but because we're talking moles here, we can use half a mole. And I would make what? So I use a mole of hydrogen, half a mole of oxygen, and I will make how much? 1 mole of water. Good. This would be about 18 grams of water if I was going to weigh it. When I do that, what happens? Yeah, it lets off heat. Specifically, how much heat? Good. For every 2 grams of hydrogen I burn, I give off 242 kilojoules of heat. That's quite a bit, by the way. This is an exothermic or an endothermic reaction. All right, so this is exothermic. All right, and what we can say is this. For every 1 mole of hydrogen gas burned, 242 kilojoules of heat is released. Now, the way we would express this is we would say the enthalpy of this stuff has changed. Now, what had more enthalpy? What had more internal energy? The hydrogen and the oxygen we started with, or the water we ended with? What had more energy inside of it? This has to have, because by the end, it's released a bunch of energy. Where did that energy come from? It has to be the energy these things started with. So if it's given away energy, this chemical compound must have less energy than this did. Water must be less energetic than the hydrogen and the oxygen it starts with. Does that kind of make sense? If it released a bunch of energy, that energy had to come from somewhere. It came from the hydrogen and the oxygen. If it's been released, do the hydrogen and the oxygen have it anymore? No, you can't eat your cake and have it too, right? But once you've released the energy, you don't have the energy. You'll note that that's the expression said in a way that actually makes sense. Right? They always say, like, you can't have your cake and eat it too. But that's not what that expression means. What the expression means is you can't eat your cake and still have it. Right? Anyway. But once you've eaten it, it's gone. Yeah.
Well, it makes equal sense. It's just a weird way to phrase it.
Yeah, it makes equal sense, but it's not in nasty backwards Yoda speak. All right, and the way we would say this then is the change in enthalpy is 242 kilojoules, but keep in mind, those chemicals, do they have 242 kilojoules more than they started with? They have 242 kilojoules less than they started with. So the delta H is negative. All right? So exothermic reactions have a negative delta H. In which case, endothermic reactions would have positive delta H's. Because when we talk about enthalpy, when we talk about H, we're not talking about the energy in the environment. We're talking about the energy in the chemicals. And in an exothermic reaction, the amount of energy in the chemicals is decreasing because it's releasing it as heat. So the enthalpy, the H, goes down. So the delta H is negative. The change in energy is a decrease, not an increase. Now, when we give you the molar enthalpy, this is a way that we describe a chemical reaction. So here, for example, we have water from a liquid becoming water as a gas. What do we call that? Yep. What do we call that process of taking a liquid water and making it a gas? What do we call it? Could be evaporation, definitely. It could also be like boiling. And the general catch-all term for that in chemistry is vaporization. It's taking a liquid, making it a vapor, vaporization. I don't love that term, but there you go. Now, in this case, when we take that water, what do we have to do to make it become a gas? Got to put energy into it. What do we call that?
Evaporization?
Yeah, but is it you're right. Is it exothermic or endothermic? Ooh, I've got a disagreement. I like it. Yeah, we'll get the boxing gloves out. Whoever wins, that's just the new definition.
Well, it's kind of like 4 against 1.
So this liquid water, is it going to have more energy in it or less energy in it by the time we're done? Good. Less energy. Good. So we have to put energy in. So this is endothermic. Now, obviously, the answer is to the right, but the delta H, that water, is its amount of internal energy going up or going down? It's going up. So it's got a positive delta H. Delta H in this case is positive 40.8 kilojoules. And we can say kilojoules per mole because it's a molar enthalpy. Does that make sense? So when we express delta H's, we are typically going to express them in kilojoules per mole as molar enthalpies. Now, we can say that because how many moles of water did we use? 1. Okay. These are obtained empirically. You are going to do a lab like this. Maybe by the end of this week, certainly by the beginning of next week, we're going to get a calorimeter, which may look an awful lot like a styrofoam cup, because I'll tell you the proper calorimeters, they're looking a little sketch baggy, but I'm going to try to repair them. But if they don't, you're going to get a styrofoam cup, but we're going to only refer to that styrofoam cup as a calorimeter. We're going to talk about it like it's a very high-tech piece of equipment. And you're going to do a lab where you use known amounts of chemicals you find the temperature change, and then using yesterday's ability to know how much it takes to change the temperature of water, because you know the specific heat capacity of water, we can figure out how much heat was actually released by a chemical, and we could come up with these numbers. By the way, this is endothermic, which means that this should make the environment colder. Maybe you've experienced this. Yeah, to some extent, but
it's colder in here than it was walking.
What do you feel? That's false. What do you feel when you get out of a hot shower in the morning? Cold, especially if you accidentally left the window open. Why?
Why did you leave the window open?
Why? You're covered in hot water. Why would you suddenly feel cold?
Because the colder around you cools you down.
But why? I mean, you're covered. We know that it takes a lot of heat energy to cool water down, and you're covered in hot water. I mean, here's the deal. If you were covered in a hot blanket, the wind wouldn't cool you down. And interestingly, it takes as much energy to change the temperature of water as it does that blanket. Why do you get cold? What is the water doing that the blanket doesn't do? Evaporating. The water on your skin evaporates, and evaporating is endothermic. Evaporating requires an input of energy. So the surroundings have to get colder. And when water is all over your skin, what is the surrounding of that water? Your skin. So what is going to get colder? Your skin. This is why dogs wag their tongues in the summer. Dogs don't sweat. We sweat. That's how we keep ourselves cool. We cover ourselves in gross, salty water produced by glands on your skin so that it will evaporate. And as the sweat on your skin evaporates, you get colder. It keeps you cool. It's not that the liquid is cold. That wouldn't make any sense. The liquid's coming from inside your body. The liquid's the same temperature as your body. It cools you down because it evaporates. Dogs don't sweat because they're covered in fur. It wouldn't be a terribly effective way of cooling down. So they flap their tongues. Air moves by, evaporates the water on their tongues, and it cools them. Pelicans. This is true. Pelicans evaporate water off their beaks, as do toucans. And this cools them. Because it's an because not all birds do that, but pelicans and toucans do. Well, often regular birds don't. I mean, for example, if you think of a bird in southern Ontario right now, their problem is not trying to cool down; it's trying to keep warm. But tropical birds need to have methods of cooling down. Birds that live in our region typically don't. They have nice light bodies, and they fly, right? Which is a pretty effective way of cooling down, right? Right? You can go up high where the air is thinner and get cooler, and you're also moving through air quickly. So they stay cool nicely that way. All right. So I have now given you here for fusion and vaporization. What does fusion mean? I thought you were just threatening to punch me if I didn't tell you. Like, I don't know, Orlando. Why don't you tell me what fusion is? I was like, oh, I'm going to tell you. I'm sorry. Well, now that I'm afraid, fusion is when a liquid becomes a solid. More commonly, we call it freezing. But fusion is when a liquid becomes a solid. And here you can see how many kilojoules it takes to make a mole of a bunch of different stuff freeze. Sodium, it takes 2.6 kilojoules for every mole of it to make it go from liquid to solid, which is not much. The same for chlorine, sodium chloride. Now, on the other hand, vaporization is when what? A liquid becomes a gas. And you can see that these require, and I should mention as well that these can go the other way as well. This could be a gas becoming a liquid. Just keep in mind when a gas becomes a liquid, that energy isn't absorbed, that energy is released. Okay. Now we can use these then to do calculations. We can use these to do calculations. And we're going to break out our friend dimensional analysis. And if you have taken chemistry with me, you know that. Does Smith use dimensional analysis at all in physics? Does it come up?
We need to change our units.
A couple times we need to change units. Anyway, we will certainly use it here. But we'll slow walk you through it. So if that's new to you, don't worry. We'll explain. So I want to look at an example here. Freon 12 is a common refrigerant that's vaporized in tubes. And it releases heat. All right. And what it does, it's actually, this is, I wrote this, so I'm only criticizing myself here. But specifically what it does is it vaporizes this on the back side of the fridge, which is why if you put your hand behind your refrigerator, it feels warm. Then it takes that thing, the surroundings have become warm, it pumps it inside the refrigerator where it does the reverse, and it's going to make it cool. Then it goes back outside, and it just constantly cycles this. So it does the exothermic portion of the reaction outside the refrigerator next to the fan, radiates that heat off. And then it does the endothermic portion of the reaction inside the refrigerator next to the fan. And when you combine these two things, you get the back of the fridge getting hot, getting rid of the heat, and the inside of the fridge getting cold. Makes sense, right? Let's talk about the math of it. So Freon 12 has a molar mass of 120.91 grams per mole. All right, that means every mole of this stuff weighs 120.91 grams. I'm going to highlight that. And the question is, if I take 500 grams of this stuff, oh, my pens have changed. That's okay. If I take 500 grams of this stuff and vaporize it, the question is, what will be delta H? Does that make sense? So, what are we actually starting with here? We're starting with 500 grams of Freon. And eventually I want to know what? I want to know delta H. Delta H is the change in enthalpy, and it's measured in what? Yeah, joules or kilojoules. In this case, kilojoules. So I'm going to want to know kilojoules of energy at the end. Does that make sense? Okay, so with dimensional analysis, our approach is always to work with units, right? So we're going to take this and multiply it by a fraction, and we're going to cancel the units we don't want and put new ones there. So let's map this out. We're going to start with a mass measured in grams of Freon. And what am I going to convert that to? And if you took grade 11 chemistry, you should know that the answer to every question is moles, right? We're going to, and what letter do we use to talk about how many moles we have? N, very good. So we're going to figure out how many moles of Freon we have. And then once we know how many moles of Freon we have, we can go look at this chart. And this chart will tell us that for every mole, we release this many kilojoules. Does that make sense? So it's kind of like a series of steps we follow. So we're going to figure out, start with the mass, figure out how many moles we have, and then from that, we can figure out how many kilojoules of energy were released. We can do this because we know how many grams are in a mole. And we can do this because we know how many kilojoules each mole releases. Does that make sense? Tell me if it doesn't. Tell me if I'm going too quick. And don't worry, we're going to do a lot of this week. All right, lots and lots and lots. But for those of you wondering when would math rear its ugly head again, when would the mole make its triumphant re-entry? It has returned. Okay, so with dimensional analysis, we start with a given number. You could actually start this question with any of the given numbers. My rule of thumb is always start with like the physical thing you have. In this case, the physical thing we have is 500 grams of freon. That's the thing, right? Whereas like when we talk about a molar mass, that's not a physical thing. That's like a proportion. That's a constant, right? But we don't want to talk about grams of freon. We want to talk about moles. So with dimensional analysis, it's always multiplying by a fraction. On the bottom of that fraction, we're always going to put the unit we want to cancel. So you might want to put a little reminder here. We put what we start with, we multiply it by a fraction, and we put the unit to cancel on the bottom, and we put our new unit on top. And before you put any numbers, just put the units. So in this case, what unit do I want to cancel? Grams. That's our old unit. And instead of grams of freon, I want to know moles of freon. Only once you've put the units in place, now ask yourself, do I have a number for that? Do I know how many moles of freon are in a gram? Or do I know how many grams of freon are in a mole? Do I have a number for that? So do I have a number for that? Yeah, specifically, it is this one. 120.91 grams of freon is 1 mole. And so we put that in. Now, keep in mind, it's 120.91 grams of freon that are 1 mole. And last semester, for those of you who are with me, we said the trick to this is always say it out loud. Because if you've put it in a way that doesn't work, it will read stupidly. Okay? So ignore me for a second. I'm going to erase this and make a mistake. Don't write what I'm about to write because it's a mistake. Okay? If I put it like this, I would say 120.91 moles of freon weigh 1 gram. Does that make sense? If you remember back to grade 11 chemistry, the lightest element is hydrogen, and 1 mole of it weighs 1 gram. So there's no element where 120 moles of it would only weigh 1 gram. That doesn't make sense. So when you always say these fractions out loud, it becomes a lot easier to work with. 1 mole of freon weighs 120.91 grams. Have I changed that number in rewriting it, or did I get it right? Is that correct? All right, what units cancel? The whole point of dimensional analysis is because we're multiplying and dividing, we can work with the units. So grams divided by grams cancels with one another. And if I stopped calculating now, I would know moles of freon. I would know how many moles of freon I want. But is that what I want to know? What do I want to know? My final end game is to know delta H, which is measured in kilojoules, right? So the nice thing about dimensional analysis, why we use it, and why I hope you'll agree, if you were with me last semester, that once you get used to it, it really is an easy way to work. And why, if you're new to this and you didn't learn this in grade 11 chemistry, I'm sorry to throw something new at you, but we'll get tons of practice this week. If it seems a little foreign now, just bear with me. Trust me. Once you get used to it, it's a nice, intuitive way to solve problems. I didn't learn it until first year university. I wish I'd known it sooner. I can do this again. Now, what unit do I want to cancel? Yeah, I want to get rid of moles of freon. Where am I going to put that? Down on the bottom, because that's the unit I want to cancel now. And I want to replace it with kilojoules. Now, do I have that number? How many kilojoules are released when we vaporize a mole of freon will be found on the table I gave you on the previous page. So go ahead and look it up. Don't shout it out. Take a minute. And I want you to try to put the numbers in this fraction, putting the numbers in the right place. Remember, talk through it. Say it out loud. I don't know what the number is. Say it was 12. Is it going to be 12 kilojoules released when we vaporize 1 mole of freon? Or is it going to be 1 kilojoule released when we vaporize 12 moles of freon? Again, I don't know the number. You have to look up the actual number. But the question is, what number goes here? What number goes there? Take a minute and fill that out. All right. Good job. Good. Very good. Very good. Very good. All right. So you looked it up on the previous page. What is the number? I can't read that. 34.99? Great. It takes 34.99 kilojoules per mole. And when we say per mole, we mean per 1 mole. Every mole of this requires a kilojoule of energy. Now, what units cancel? Moles of freon cancels with moles of freon, and I will be left just with kilojoules. All right, so go ahead and do that calculation. Go ahead and do that calculation. And by the way, if you're wondering how to do it, just multiply by the numbers on the top, divide by the numbers on the bottom. So it'd be 500 times 1 divided by 120.91 times 34.99 divided by 1. Just go through and follow it. Take a minute. Let's make sure everyone gets it. This should be on the order of like 135 or so. Is it a little more? Oh, right, of course, because that'll be a bit more than 4. So are we talking like 145-ish?
Oh, yeah.
Yeah?
Almost exactly like
144.6944. Okay, and I'm just going to round this to the nearest whole number, so we'll call it 145. Again, we're going to go over rounding rules later on, so don't stress about it too much right now. Yes, ma'am. Yep. And so we can say when 500 grams of freon are vaporized, (145 kilojoules are now what? Absorbed or released? So vaporizing, let's go look. Is vaporizing a positive or a negative delta H? Positive. Is that releasing heat or absorbing heat? Absorbing. The surroundings get hotter or the surroundings get colder? Colder. So 145 kilojoules are absorbed. Now, vaporization, we said, refers to the barrier between liquid and gas. I wasn't specific here for this question, so I'm going to be specific. All right? So here we are talking about water as a liquid becoming water as a gas. Which side does the energy need to go on for this to happen? Do we put water in, or do we put energy in, or does energy come out? Yeah, we have to put energy in. And so is this one going to be a positive or a negative delta H? Positive. Is it exothermic or endothermic? Endothermic. Would the surroundings become hotter or the surroundings become colder? Colder. Even, by the way, even when you boil water on the stove, we may think, oh, that makes the room hotter, not colder. But only because you've got the stove on, right? You can test this. You could start with the room in a neutral state, turn the stove on with no water on it for 10 minutes, see how much the temperature goes up. Then, give it an hour or two to get back to normal, turn the stove on, this time with a pot of water on there, and measure how much hotter the room gets in 10 minutes. And you'll find that with the pot of water on there, it keeps the room relatively cool. because that heat is being used to boil the water instead of just being released into the atmosphere. Does that make sense? Okay, try this question out. Yeah, try this question out and we will pick up on it tomorrow. But try it now. You got a couple minutes left to get started. So at least try and set it up. By the way, I was kind of egocentrically forgetting that not everyone in this room took chemistry with me last semester when I kind of planned my unit out. Would a day on dimensional analysis just as a tool be useful? Yeah? Okay, let's do that. Let's do that Wednesday. So tomorrow we're going to carry on with this. And then let me mark this in my calendar. In fact, don't even try this question right now. Let's work on logistics here. So tomorrow we'll finish up this note. And then I think Wednesday we will devote to dimensional analysis and to significant digits, which is like rounding rules.
Can we do it on Thursday so I don't miss it?
Right. Actually, let's do it Tuesday. Let's do it tomorrow. That's fine. So tomorrow we're going to take a day out and we're going to talk specifically about pure math stuff, just the math of chemistry class, how I want you to approach it. Does that make sense? Okay. I should have thought of that when